Okay, good. Looks like we've hit the top of the hour here, so I will go ahead and get things rolling. And I'd like to thank everybody here for participating in this Keysight ElectroRent Power Sensor Application webinar. Most of us really, I guess, kind of think of power sensors as sort of the equivalent of a DMM for RF, and hopefully today you'll learn a little bit more about those solutions and other ways to be able to use those, and some applications for those. So with that, go ahead and go to the next slide there, Antoine. We're doing this, as I mentioned, in conjunction with one of our distribution partners, or actually a distribution and rental partner. It's ElectroRent. They helped co-sponsor this event, and some of you may have actually gotten some invites from them. You go to the next slide. ElectroRent is, as I mentioned, is one of our distribution and rental partners. They offer a whole range of solutions for anybody interested in instrumentation, test instrumentation, both rental and financing options they offer. They have, I think, oh, there it is on the slide, $1 billion in global inventory. So they are a global player in that marketplace. In addition to providing financing either through renting or leasing, they also provide new equipment, and they offer the whole range of Keysight's distribution products, and are actually one of our larger stocking distributors for those products. So you'll, in fact, the power sensors that we're talking about today are products that they keep on the shelf and can be purchased through them. They are also take care of certified owned, so they as equipment ages out, they actually sell their old inventory, and so for some of you that may be looking for lower cost solutions, that's a way to go there. And then kind of the fourth pillar of their business is asset utilization optimization. So for people that are looking for that and trying to improve their asset utilization, that's an opportunity that's available to you. You go to the next slide. Great, so I'm going to go ahead and I'll briefly introduce myself, and then I'll introduce Antoine. So I've been with Keysight for about 7 years. I've been in the test and measurement business for multiple decades, as you can probably see from my hair. Have been doing this for quite a while. Work almost exclusively with our distribution partners like ElectroRent, helping them in terms of satisfying a lot of what will be more the general purpose types of applications out there. Antoine, who's going to be doing the bulk of the presentation, is originally from San Juan in Puerto Rico, and although most of his time has been spent in the Boston area, although I found that interesting because I detect neither a Boston accent or a Latina accent as he talks.
Yeah.
So we've done a good job of I guess, picking up the California lifestyle there. He earned his both master's and bachelor's degree at MIT back there, and has been in the military and aerospace and defense industry for 12 years before coming to Keysight. Has spent a lot of time in the lab and is really excited about the opportunity to be able to help people and share his experiences and learning both from his time in that role as well as here at Keysight. So one more slide, and then I'm going to turn it over to Antoine. And really just some logistics. At the end of this webinar, when you log off, you'll actually automatically be launched into a survey. We ask you to please just fill it out. It's I think it's only 4 questions and a comment field. For filling it out, you can see there we've got a little portable travel USB hub and one of the critical measurement tools. A level, a pen, it's actually got a ruler, it's a stylus. So anyway, fill that out. We really would appreciate the feedback, and we'll send that out to your little Keysight swag. If you don't want it, or the address that you may have put into the system was the wrong one, just go ahead and make a note of that in the comments field, and we'll respect that. If you have questions during the session, please go ahead and just type them into the chat window in the organizer. I'll be monitoring those for Antoine, and we'll interrupt him as appropriate to be able to ask those questions. So with that, I'll go ahead and turn it over to Antoine and
Keith, thank
let
you.
him go ahead and go.
I appreciate it. Well, first and foremost, welcome everyone. It is really exciting, in all honesty, to be able to connect with what are a number of new faces and also to dive into an area that in some cases is just kind of very trivial and very benign. You know, here I have in my hand a power meter. It's a USB connection. We'll be talking about these as well as LAN sensors today. And what's true is that we might often just need to be able to take a power measurement and not really think too much about what's going on inside or the additional capabilities that power sensors can provide for whether it's troubleshooting, R&D purposes, or even if you're in the production sphere. But what's very true is that there's a number of good learnings about the internal workings of these power sensors that can help you justify and structure meaningful follow-on equipment selection. And so it's from that perspective that I'm really excited today to dive into our overall topic. Now, I know we're going to be talking about power sensors, but it made sense to me to try to put this a little bit more into context about why going into power sensors matters today. Ultimately, the end goal is to help you as an end user avoid costly delays. Now, there's a lot of business and budget impact due to equipment training, maintenance, and even technical support. All of those are measurable. In a very recent past, we released a survey in which we found more than 90% of companies report a revenue loss because they're experiencing test and measurement delays or they need training or maintenance. 54% of companies report losing $100,000 or more a day while waiting to solve test issues. And to put that into context, about 89% of those surveyed who are test equipment operators required access to knowledge and portals. So we hope to be able to foster that dialogue with you today. In addition to having access to both Keith and myself, we as a company and organization are always very present. Keysight Care, sharing the number, is a real-time resource that we encourage you to use, whether it's for power sensors or any of the other products that you might already be using. And also sharing a link to our overall report. It is some interesting takeaways. So as we move through what will be the remaining slides of the presentation, I'll give a few seconds before each so that you can review the material, call it about 3 seconds, before then overlaying my commentary. What we'll cover today and what I hope you remember are the following. In part, it also serves as our agenda. Now, from an applications point of view, we use RF power sensors everywhere. Anywhere that you're doing an RF or microwave test, or if you're in a microwave RF industry, you'll need accurate and simple measurements. Now, those relate back to our power sensors. There are 3 different types. We have thermistors, thermocouples, and diodes. Ultimately, the kind of process that will flow through is that there is certainly the traditional method of considering what a power meter and a power sensor is. And you'll see that one image on the right-hand side. It'll serve as our anchor point. Well, they're helpful, and we've come a long way since then. We have types that are USB or even have LAN connectivity that pair up really well with a PC or a laptop. These provide functionality, they provide less weight, easier access for setup. And these methods are what we want to help share with you today so you can understand if you've traditionally used a power meter and power sensor, there's great benefit in just being able to have one of these devices handy. That said, these types of sensors have broad integration through our RF equipment instruments, and we'll talk about how that comes into play. And it'll be meaningful to step through 2 applications that I think many of you might have already a hand in. Within the aero, astro, and defense industries, there is always a need for remote and long distance sensor applications. We'll use the USB and LAN to go up to 90 meters. And in space environments requiring TVAC testing, we have options that fit right inside. So again, as we move through, we'll be talking about our traditional methods, our power sensors that integrate with our laptops, and the connectivity that can range as far as 90 meters. So let's start. So usage. We are always interested in being able to correctly and accurately measure power, and we can do so with other pieces of equipment. Why would we consider a dedicated power sensor or power meter and power sensor setup? Well, for starters, it's easy, it's simple, it's low cost, and it's accurate. Now, you might already have existing familiarity with using a spectrum analyzer, an oscilloscope, or maybe even a network analyzer to collect power measurements. And in their own right, they do a great job at giving you a approximation to your power. They have sensitivity on the orders of tenths of a dB, and they're frequency selective. If you're in need of being able to collect even more accurate data, without question, a power sensor is the way to go. It has sensitivity on the hundredths of a dB or better, and you can measure higher power. It does come at the expense of frequency selection, but for your applications, that might be good enough. We show here our traditional technique, and we've come a long way since then. This diagram shows the basic method of measuring high frequency power using a power meter and power sensor. Simply, the power sensor converts high frequency power to a DC or low frequency signal that the power meter can then measure and relate back to an RF level. The meter displays the detected signal's power value in dBm or in watts. Now, the power sensors themselves, they can be one of three types: thermistors, thermocouples, and diode detectors. We'll go into a little bit more of that into the next slide. What I'd like to highlight, though, is that moving beyond the traditional method where you have a dedicated display showing you your power, we have functionality of being able to connect two different types of sensors up to a PC or a laptop. Now, I realize that it might be small, but if you kind of focus in on the laptop display, what we have overlaid there is our Benchvue software. And this is our way of being able to have our power sensors communicate directly with a platform which provides ample flexibility for further understanding and visualizing your power. We can see our power displays as an analog readout, as a digital readout. We can look at how our power varies over time, like a strip chart. And in some cases, we can view our live traces. So this gives us yet another visualization tool above and beyond what we might consider for our traditional method of just a power display. We have methods of being able to obtain even more insight to the power signals that you're already measuring. Now, overall, we have three primary types of power sensor architectures. And the reason that it makes sense to enumerate them is because it can help structure which type might be most beneficial for your intended application. So let's step through them quickly. Thermistors are a heat-based type of sensor. They're one of the earliest types by far, and they have been replaced in most applications by thermocouples and diode detectors. They are most regularly found in metrology labs where they're referencing power transfer standards. Now, as an advantage, they're very accurate and they're directly really traceable back to NIST, but they're slow and they have low sensitivity. You might see these as models hanging around in your lab as a 478A or an 8478B. They were one of the first types of sensors to measure RF and microwave power. Now, heat-based sensors, such as thermocouples, They depend on a process of absorbing all energy except for the tiny bits of inefficiencies and reflections. And the way that they measure the RF signal is by detecting the resulting heat rise. Thermocouples work as a junction of two dissimilar metals, and they generate a voltage that's proportional to temperature. This temperature is what's directly related to your incident RF power. From an advantage point, they're accurate, they have great linearity, but they're also slow and have low sensitivity. So as our best tier, we have our diode detectors, and they work by rectifying the RF signal to produce a DC voltage. They are by far the fastest. They have a wide dynamic range with the ability to measure down to -70 dBm, and that's really suited for ultra low signal detection. These can have applications like at the front end of an RF or a microwave system, and they provide very fast response times, making them important for pulsed and high data rate applications. Now, for their ability to measure low signals, they're limited by the maximum energy that they can detect, and so that leads to their disadvantage of being easily overloaded. But with care, diode detectors can also help you measure peak power in cases where thermistors and thermocouples only can really show you average power. A couple of models of those diode sensors are shown below. I'm a visual person, and so I always like referencing this graph as it relates to being able to describe the different power ranges that these sensors best operate in. At the top in gray, you can see thermistors. They work really primarily from a -20 dBm up to a +10 dBm range. Thermocouples, in which we operate them in their square law region, can go from -30 all the way up to +20 dBm. Now, if you use an extender, and in some cases you'll see big heat sinks that go on the end of your power sensor, those ranges can go as high as +44, making them very well suited to collect power measurements above and beyond just using your maybe signal analyzer, spectrum analyzer, or even a oscilloscope. Diode detectors, as I mentioned, they can go as low as -70 dBm, but they are limited in their maximum power of roughly around -20 dBm. For very specific applications, those ranges can be extended. So for CW signals, we do have options for diode detectors that go up to +20. And for modulated signals, we can add in extenders to further increase their range. But in scope, just a way of being able to think about what type of sensor might make sense for your intended power application. Our brochures do a fantastic job at also overlaying this information related to frequency and power ranges. So I thought it would be very useful to at least point your attention to this table located in our brochure, page 33, that helps illustrate the different types of power sensors based on what might be your intended application. You can see here at the top an example of a U2042 that has a 5 megahertz bandwidth, goes all the way up to +26 dBm, but has a 10 megahertz up to roughly 5 gigahertz operating bandwidth. Depending on what might work best for you, these types of tables can help you select an appropriate power meter. They make selection truly a breeze. Now, I know that we're going to be dedicating most of our time today to power sensors, but I'd be remiss if I didn't point out at least the few different types of power meters that you might see in the lab and have access to. Overlaid performance and price, we can see that we have our EPM variety. They measure average power very well, and you'll find these in R&D and manufacturing, potentially even in a test lab. We have our EPM-P series, which has also applications within the comms industry, and those can measure both peak and average. These are those older green displays. Our P series is a next step up, and they have a wider range of functionality. And if you can even see on the image, it has an overlaid trace, so you can see features such as CCDF. And lastly, a form factor that you might not necessarily have come across before are P-Series LXI. And these, again, additional ways to being able to determine if a traditional method is more well suited for your application. These are the ones to consider. Now here is where it gets a little bit more involved and interesting, certainly. From a performance and price standpoint, we have a wide variety of options. And so here, showing just a simplified overview, because I'd be doing a discredit to those brochures and tables that do a great job at illustrating this in further detail. But notice on our lower left-hand side, we do have handheld power meters that roll both elements of a display and the sensor into one. They work great up to 6 gigahertz and have a very wide dynamic range. Now, as you move across, these might be power sensors that you've come across previously. The ones that I'd like to specifically point out are our U2000 series, which have a wide dynamic range, have a wide range of input powers, and are also both USB and LAN connectivity. So we have a 33 gigahertz LAN with TVAC option. In our upper right-hand side, combining performance at price, we also have our wide dynamic range power sensors. Here in the top is our LAN version. We also have a USB version too. Now, these are fantastic from their capability to measure up to 67 gigahertz, which for many applications is a perfect sweet spot. They have the capability of measuring average power and peak power. And what's more, they also enable you to have variable sampling rate with long memory acquisition. So here we also start rolling in functionality that includes data collection, so that above and beyond just being a passive device, it's one that can also save and store data. They also have a very wide 5 megahertz video bandwidth. So based on the types of signals that you're looking at, this can be a great fit for you. So the focus of our today is diving deeper into these USB and LAN options. And we're going to highlight two, and you'll see those there at the top, the U2049XA and the L2065XT. Now, these options, they range from 33 gigahertz up to 53 gigahertz, and they have incredible dynamic range. They have the ability of doing internal zero and calibration, and they're also compliant for thermal vacuums. For our LAN, there's a little bit more to do than just connecting a cable to it. These are power over Ethernet devices, which means that they obtain their DC power supply voltage from the Ethernet connection itself. So there is one level of piece of equipment that we must add. But from a trade-off of obtaining just excellent long distance remote monitoring, they are quite an incredible device. They have best-in-class long-term drift performance, which could be very meaningful for tests that take place over long stretches of time. And as we previously noted, these have very deep memory with variable sampling rates, giving you a latitude of flexibility as it comes to structuring what type of data collection might make sense now in the short term or might need to be modified. To point out, here on the right-hand side, at the very in the middle, we have basically our ruggedized our LAN sensor, which has this kind of like rubberized exterior. This gives it a little bit more ruggedization for any types of bumps and scratches that it might endure in the lab or as you're going out to the field. At the very top is a version that goes inside the TVAC chamber. It's a little different since it needs to prevent outgassing, but in scope, very comparable overall profile. We're talking about, on the previous slide, we mentioned 33 gigahertz up to about 53 gigahertz. And if you're in the near term testing applications that might go higher, what I wanted to at least plant the seed is that we have additional models that we are releasing in the near term to help you increase those characteristics to 54 gigahertz or even 67 with very comparable performance to the prior slide. What's more, these also have real-time measurement with 0 dead time to ensure that every single continuous pulse is measured. So as your needs evolve, certainly consider that the existing product line might be a fit, and for additional questions or even just ways of interfacing them together, let us know, reach out. We're also happy to comment on those that we'll have in the near term with partners like Electrorent to be able to help share those most directly with you. Now we talked about a bit LAN. I wanted to reference the USB series, and that's really one of those examples that I have here. It fits pretty neatly in the palm of my hand. It weighs, I don't know, a few ounces. They form their connection with a micro USB on the input, which connects up to at most a 5-meter long cable to your computer. Now, what's great is they're small, they're lightweight. These have 24 gigahertz of a frequency range, and they offer quite a dynamic range of input powers. They're sturdy, and they also come with built-in triggering. This could be very significant for trying to align data collection points based on your setup. And another useful feature for how power sensors are more than just a device which passively senses power. They can be synced up and their outputs can be really well visualized using our Benchvue software. Now, in some sense, a little bit of the nitty-gritty on details, but what I'd like for this slide to highlight is from the standpoint of being able to adjust a sampling rate and have internal memory on your power sensors, you can really move away from a more traditional setup where you might have needed to cascade together multiple sensors using DACs. Where possible, we really do enjoy and really strive for simplifying and easing the burden of test measurement, as well as decreasing the sources of uncertainty. So with a device like this, which can sample and can store, it can open up a great deal of flexibility for both troubleshooting, as well as you move over to any type of production setting. This USB example also has a trigger in and trigger out. Mine, for example, only has a trigger in. This slide shows that you can also enable two-way triggering. So yet another way of layering on more of a sophistication layer to your existing setup. So these sensors are great in their own right, and I've chatted about how they can connect up to your computer. But what's also really significant to realize is that each one of our pieces of equipment within our product family of network analyzers, signal generators, spectrum analyzers, come equipped with built-in software that can support this USB power sensor. So what's particularly incredible is that if you are using power sensors and power meters in your lab to interface or monitor a signal generator, or let's say coupled with a network analyzer to do any type of source power calibration, these sensors can replace both of those items. And what's more, above and beyond those units which usually interface with GPIB, the USB protocol also helps your test setups go even a touch faster. Truly wide-ranging and truly a way of interfacing across any product families. This enumerates a little bit more of what I had gone into. So for network analyzers, you can perform source power calibrations accurately for tests like gain compression or intermodulation distortions. On our ENA offerings, we can do scalar analysis or frequency conversions. On our handheld devices, we can turn into a power meter with the built-in user interface. And even extending through towards our field Fox, we can turn it into a power meter function. So let me help contextualize this by showing a little bit more about our Benchvue software. Benchvue is a contained platform that you can download and install onto your computer, and it allows for easy viewing, capturing, and exporting of data with quite a number of customizable visualizations. So let's take a look at the image on the left first, which shows just a feature of observing our power in either a digital meter perspective, an analog meter to show you an overall range, or perhaps even you'd like to see how power has changed over time, and that can be performed with a data log. On our right-hand side, we show how we can overlay even more functionality using the trace view. Here you can get a sense, broadly speaking, of if you were measuring pulses, how those pulses look over time, and characterizing them with some very handy math that Benchvue does the heavy lifting for you. So quite an incredible piece of software that really helps transform just a otherwise passive device or power sensor on an older display into something that can help you glean much more insight out of your existing setup.
Antoine, there's a couple of questions just about Benchvue, and I'll kind of answer them broadly.
Sure, that's great.
Yeah, Benchvue application for these products is actually for the power sensor is actually included with the product. So, so you don't have to go buy additional software. It's a pretty easy process. If you go onto Keysight's website and search for Benchvue included, you can get more information on that process. But essentially, if you have one of them, you plug it in, it'll enable you to be able to download that and license it. So pretty simple, and it's included with the USB and the LAN power sensors.
Yeah, what's more, connecting up any power sensor, Benchvue will recognize the specific model, serial number, and details of your meter. It's just as easy as plugging in.
There were another couple of questions not really tied to Benchvue, but since I interrupted you, yeah. The slides will be available. We'll be sending out a thank you. I don't know if we'll be including them or providing a link, but they will be available. Also, a recording of this will also be available. So if you want to go back and listen to it again, there'll be a recording that you can stream.
Right. Our intention isn't for any of this information to be flash memorized, but really to serve as a touch point, to serve as information you can reference when it becomes relevant. So we're cognizant everyone has their own scope of kind of work. For those who might have been in the lab, they might now be doing more design related work, or people might be stepping into the lab in the near term. So our goal really is to help build additional confidence and to be able to at least have some resources handy and at the ready. So for when the time is right, you can more confidently turn back to those details and say, oh, right, I remember this. Let's kind of poke at it a little further. That's great.
Had another Benchvue question. So
Sure.
and I think this is going to be for both USB and for the LAN-based ones. Can you also control it using Skippy commands? Treat it just as a regular ATE type of piece of equipment?
That's a great question. Offhand, I don't know for sure, but I will take the action to find out and be able to relate back.
Actually, I do. 100%.
Excellent.
Yeah.
I think you'll find.
Same Skippy commands. It's pretty ubiquitous. You do get some advantages too of just speed, because now you're not going through TPIB.
Sure thing. But really, no code required for being able to collect all of these different types of measurements. So for those who have maybe moved away or don't want to necessarily dive into writing, sending, and controlling Skippy commands, the GUI is very straightforward and very easy to learn. Here's where we'll start chatting about our two distinct applications. And at first, we'll talk about our LAN power sensors. So as noted, our LAN sensors require a power over Ethernet to supply the DC voltage required to operate them. And what I cared about showing was displaying three different types of configurations to help you visualize how that might be helpful for applications that can appear for you in the near term. So starting with our bottom rightmost image, with the PoE injector, you can easily have just two ports, your data in, your data out, and power out by connecting the PoE directly to wall power. This is an example of just using, for example, one LAN sensor. With a PoE injector, you could also cascade it to a LAN hub or switch. So you can start moving towards still using your PoE injector, but cascading multiple together. And last but not least, top left corner, being able to show that if you have a PoE switch, then you can provide all of that power from one device and cascade multiple LAN sensors together. And as you can see, the overall architecture and the benefit, now you can start integrating into your overall intranet, where you can control and monitor these sensors from your laptop, a computer, or remotely from your workstation. And it provides a great deal of latitude above and beyond what might have otherwise been your short limitation on a power meter attached directly to a power sensor. So let's chat about an example. Here, the overall intended application is to be able to monitor a radar antenna tower from a control room. Here, some of the pulse measurements might be rise time, fall time, confirming pulse widths and power. But what's true is that there is a long distance between the radar and the control room, or at least where you're going to be situated. Now, in any normal SARMs, the USB power sensor has a 5-meter limitation, and this relates just back to the USB protocol. So in this case, if you could be 5 meters close to your radar tower, then this might work. But in general, it's pretty much the limitation of this application. Now, if we were further away, maybe the first thought process would be to use a long RF cable. And while that will still form your electrical connection, you can imagine the drawbacks of using this are accounting for the large loss that you have in whatever distance of cable you're using, as well as the uncertainties now due to your mismatch, routing, RF cable not always necessarily easy to work with, and if it's especially low loss cable, that ends up being thicker diameter cable, which is even a little bit more challenging to use. So not so streamlined or glamorous for a setup, but along comes being able to use our USB and LAN application together. So for using our USB sensor, we can make our measurements as close to our radar antenna tower as possible. We'll still port back over that 5 meter limitation, but in this case, we'll use a USB to LAN hub. Now this interface lets us couple our USB connections to our hub, as well as then interfacing the long LAN cable that will feed back our computer in our control room. This greatly eases up the burden of what was previously loss associated with cable and a much easier setup to manage. We can go and develop this one level further, that with a hub, we can cascade multiple channels together. Now here, the theoretical upper bound is about 128 devices, but there will be some upper threshold where timing issues will start to drive your full number of USB sensors that you can use. But we've successfully showed that you can cascade 20 of these together and really have a robust setup. And what's more, Benchvue also helps you do multi-list views in channel mathematics. So you can actively monitor and coordinate all of these devices simultaneously within the Benchvue application. If we wanted to pursue a straight up LAN application entirely, we actually get a much simpler setup. So recalling using your power over Ethernet injector, here we can have our LAN sensor as close to our DET as possible, mating our connection, and running up to 90 meters of LAN cable, which provides a great deal more flexibility. It's an easier setup, and it's also very robust. Quite a difference when compared to what traditionally was a 5 meter limitation. Now you can concurrently run devices together and greatly ease up the burden of making accurate measurements. And what's more, if you were to cascade a power over Ethernet switch, you can develop out a multi-channel scheme very similar to the USB method. So here, additional ideas of how we can take something that was traditionally a very close to DUT power measurement scheme and port it over to giving you the ability of making measurements across larger distances. And what's more, maintaining accuracy and reducing other sources of uncertainty. We'll next dive into our second application of TVAC. Now, TVAC chambers, these are used to simulate the conditions found in upper atmosphere and outer space. They can be as wide and large as capsules here shown in the image. Their goal is to simultaneously control pressure and temperature. If you've had the fortune of seeing one of these live, you can appreciate that they are very robust devices. Think of an oven chamber like a Tenny, but taken to an extreme. Their job is to expose these components and systems to vacuums and extreme temperatures. Well, the most common TVAC examples relates to tests where we're looking at satellite performance, where we're looking to control thermal cycle and testing of components and their subsystems, and in some cases testing complete satellites. And the desire is having a fully controlled environment. So as you can begin to see here, with the care that's needed to preserve both pressure and temperature, we can start forming a conception of what type of setup you'd have. So for our first image here, with your device on the inside of your TVAC, you are really porting out measurements from the internal of the chamber, running wires, runs, switching matrices to reach your end pieces of test equipment. Here I'm showing how the power meter and power sensor, at least the traditional method, would sit right outside and basically be at the furthest away from your TVAC chamber. We'd be going maybe through a switch, we'd be going through some type of interface, and an appreciation for distances, to put this into context, somewhere on the order of 40 to 80 feet wouldn't be uncommon. As you can see here, for our devices under test being inside the thermal chamber and our reference plane for our device measurement being so far away, there are a lot of cable runs and areas in which we would really need to work quite aggressively to compensate for those uncertainties and areas in which the power that's being measured is not directly the power that's coming out of our ducts. So how can we take this one step further? Well, imagine if you had a device that we can just sit directly on the inside of our chamber. We've now moved our reference plane, instead of being so far away, directly up to the device under test. So here what's circled is that we can put devices, not necessarily this one, but similar form factor, directly inside our TVAC chambers, and we can directly monitor our power with functionality like internal zeroing and calibration, and also with minimal drift. You can gain an additional appreciation of how your accuracy is improved while reducing your uncertainty. And just as before, we would now leverage the power and the interface of Benchvue sitting on a computer that you'd already be using in your setup to control and monitor the TVAC sensors themselves. Our advantages, I think, stand out in simplifying your setup, as now you're connected directly within your environment. You benefit from remote monitoring. You can connect to your network and control things remotely anywhere in the world where you have a web browser and your Benchvue software. And the reliability and accuracy of your measurements. By eliminating your long RF cable, you're removing your power measurement uncertainties due to insertion loss or poor visual matching or even temperature effects. To determine what's the right option for you, I think there are a few elements to consider in your overall checklist. What do you know about your signal up front? Sometimes you do have an understanding of power level or type, whether it's CW, average, or peak. Format, are you testing only CW signals, or are you testing some type of modulated signals? And bandwidth. We have great brochures like that listed on the right-hand side to help you identify what's the right power meter and power sensor. We step through those capabilities, considering what sensor technology works better for your application, and now providing you the flexibility of considering a USB or LAN option for your intended use case. And to expand and go one level further, we can also help you optimize for speed, accuracy, and cost. What to remember from today? Well, this is the same slide as we had up front, so I hope these anchor points help navigate our overall deck today. What I'd like you to remember is that RF and microwave applications all require some level of RF power sensing. So across a wide range of applications, power sensors come into play. The three types to remember: thermistors, thermocouples, and diodes. The ones you'll almost certainly encounter are thermocouples and diodes. Power measurement methods, we talked about our traditional power meter, power sensor. Well, we can now port over and really leverage the Benchvue platform using a computer to connect your devices through USB or LAN. Or perhaps you're using a Keysight piece of test equipment already, like a network analyzer or a signal analyzer. Those will also interface well with your USB or LAN sensors. And lastly, as the two applications in which we jumped on, long distance applications greatly benefit from the USB LAN combination, giving you flexibility of up to 90 meters. And for environments in which pressure and temperature are of tantamount importance for your gut, we have TVAC options to help you install those directly into your setups. So as I said, our goal to create additional touch points and to help develop that understanding when relevant, we have a number of great resources that I'd encourage you to use. We have webcast series and on-demand learning on keysight.com. We have our Learning Center, which has many topic areas of RF fundamentals, including power meters. They're excellent pieces of materials. We have our University Engineering Essentials, which further elaborates on how we partner with universities. Perhaps you're joining us as far as some type of internship. Keysight Care, always available to answer your questions. And last but not least, a couple of application notes that might help you when the time is right. Brochures, steps for making better power measurements, and 7 good practices to preventing damage. I've included the data sheets for those 2 models that we referenced today so that you can refer back to them when it makes sense. With all of that said, thank you. That certainly wraps up the webinar portion that I wanted to present to you today. So with that, Keith, I can hand it back over because we've got a few minutes for the top of the hour. We're delighted to take any additional questions and answers and to expand on any topic areas that are top of mind for you.
Terrific. Thank you very much, Antoine. Every time I watch one of these or sit in on one of these, I learn a little something, so I appreciate that. If you have questions, feel free to type them in the chat, or you can unmute yourself by clicking on the gray microphone and turning it green and ask a question. We'll stay on here for either another couple of minutes or until there aren't any more questions. So feel free to enter something, as I said, into the chat, or go ahead and unmute yourself and ask a question. Everybody is shy.
It's okay. I can certainly say that, you know, the notion of power sensors is uniquely fascinating. I know that for at least many people, those that you might have exposure to might just be those pieces of equipment that you have in the lab or from an adjacent colleague. I know, Keith, that we mentioned references to electro-rent. And so there are ways certainly where we can chat about and provide maybe even a demo or an evaluation to be able to facilitate helping you understand what type of power.
Let me know, and then I'll go help you right away.
I wasn't sure if somebody had a question there or not. Well, as you are disconnecting from the session, please fill out the webinar. We certainly would the survey for the webinar. We really appreciate the feedback. If you have other things that you'd like us to do webinars on, please do include that in the notes there and the comments. Yeah. We value that. Well, I don't see any of the questions, and it does look like people are starting to disconnect. So for those of you that have typed thank you, you're welcome. Glad this, hopefully this was valuable to you and you got something out of it. Again, we appreciate your time and the opportunity for you to learn more about solutions Keysight has, and and hopefully consider us for future needs that you have. Thank you.
For sure. Feel free to reach out. Take care, all.
Take care.